When you look at something like a title that says using multiple representations to solve problems, that multiple representations is really talking about stories. This is what we've got right now as a story, equation, table, and graph. And so we're going to use this story to come up with an equation, table, and graph. And those are the multiple representations in general that we're talking about when we say multiple representations. So when I see this story, it says Tim is 210 miles into his 525-mile trip to the Grand Canyon when he stops to gas up and get something to eat. He had been averaging 70 miles per hour. So the first thing I look for is a unit rate. And that unit rate, can you find it? It's right here. You look for the per. The per, the each, the every, there was another, maybe to the, like if he's getting 30 miles to the gallon, that's kind of an each or an every. So here's our unit rate, and they may not give you a unit rate, they might give you a rate, something like he went 210 miles in 3 hours. Well, there is a rate. It's a comparison of two numbers with different units. Well, if he went 210 miles in 3 hours, you can pretty easily figure out, dividing 210 miles by 3 hours, that he's going 70 miles per hour on average. And that's what this says, is he's been averaging 70 miles per hour. So my unit rate is 70 miles per hour. And the reason I look for the unit rate is because it's going to tell me a lot about the other things that I do need to know. For instance, we want to identify the two quantities that are changing in the situation. We want to identify the independent and dependent quantities. We want to define variables in order to write our equation. Well, in the unit rate, there they are. Now, you can probably logically figure out that the distance he's going and the amount of time he's driving are what's changing. Well, that verifies right here, miles, that's the distance he's traveling, and hours. Those are the two quantities that are changing. But now we need to decide which is the independent and which is the dependent and define the variables. Well, again, right here, if you have a unit rate, the first unit depends on the second unit. The number of miles he goes depends on how long he drives, specifically 70 miles per hour. So that's what I'm going to write. So again, miles dependent, hours independent. And you'll notice that I didn't just write down miles and hours. I want to say what miles measures, and I'll show you why when we get to the table. So it's distance in miles, and what hours measures. Hours measures time, so time in hours. Now, our dependent is always our y, and independent is always our x. So I'm going to put that x equals the miles, and time. Oh, I said that. I did that backwards. Let's try that again. So dependent is y, so the distance is y, and then the time is independent, and that is x. We've defined our variables. We've identified the dependent and independent variables, and we have identified our unit rate. So now for our equation. Well, again, distance depends on everything else. So y, the distance, equals, well, he's already traveled 210 miles. So we're going to start, and so this equation is really starting from when he, after lunch, when he begins his trip again after gassing up and getting something to eat. So the 210 miles he has already gone, and that to that we're going to add 70 miles each hour. And that each or that per also indicates that this is the number that's going to get multiplied by the variable, and usually the x. Well, almost always. I can't think of a time it wouldn't. So your unit rate, that's the other nice thing about the unit rate, is it tells you what number is going to be multiplied by x in your equation. So what if they ask you something like, how far will he have gone in 3 more hours? Well, so when it says 3 more hours, we have to recognize that 3 hours, well, if you'll remember, hours is the x. So they've given us an x value, because they could have asked something like, how long will it take him to go a total of 300 miles? Maybe we do that one here in a minute. So this is our x. So we replace x up here with 3. So y equals 210 plus 70 times 3. Well, 70 times 3 is another 210. And so in another 53 hours he would have gone a total of 420 miles, which means he's only a little more than 100 miles away, and we really should put our unit on that. He's only a little over 100 miles away from the end of his trip. So again, let's go with, what about the other question? What if they said, how long does it take him to go 300 miles? Let's try that again. So we have to recognize that they have now given us a y value. So we replace the y with 300. So 300 equals 210 plus 70x. So now we isolate x by inverse operation. We need to start by subtracting 210 from both sides, which leaves me with 90 equals 70x, and then we divide both sides by 70. And that becomes 1 2/7, or approximately 1.3 hours, because remember we found the x, and the x represents time in hours, and we specified hours, so that's good. So now let's fill out the table. So the table might look something like this. Now what confuses students a lot is, what does it mean right here, quantity? Units of measure we get, and a lot of times students want to put, time, or let's see, hours and miles because of this miles per hour. So actually the independent we know is the hours, so they want to put hours here, and the dependent then they want to put miles. But then when they see units of measure, they realize, wait a minute, the units of measure, now here's where hours goes, and this is where miles goes. So then what are these things? Well, this is exactly why I wrote time in hours and distance in miles. And that's really what you need to put in those spots. The variables we had already decided on. Of course, independent we know is the x, and the dependent is the y. Now probably in your table you're going to have some numbers already put in there. And if you're lucky, they'll be ones you've already calculated. Now this 0 right here, if we were to put it back into the equation, remember he's already gone 210 miles. The equation we wrote was from after he gassed up and got something to eat. So at 0 hours after he gasses up, we're at 210 miles already. Then of course after 3 more hours, then he's at 420. And then we already calculated the 300. That turned out to be, if we round it, 1.3, or 1 2/7. And then the 525. So really what they're asking is, how many more hours is it going to take him to get to the Grand Canyon? So again, we plug this back into the equation. So y equals 210. Oop, it's not, well, that's our equation, equals 70x. And then which one have they given us? Which variable have they given us down here? Well, you can see it's the y, so don't plug it in place of the x. That's a common mistake, is if we stop thinking about what we're doing, we kind of tend to automatically plug numbers into x, and sometimes it's appropriate because they are x numbers, or they go in place of the x, but in this case, these two go in place of the y. So that's what I'm going to replace. So 525 equals 210 plus 70x. Again, I subtract 210 from both sides, and that is 315. And then we divide both sides by 70 to isolate the x, and that equals 4.5. Again, since that's the x, that's hours. So he has 4.5 more hours to go to get to the Grand Canyon. Now, what was his total trip? Well, like we said, looking at the 210 miles he's already gone, if he had been averaging 70 miles, well, then he's already gone 3 hours. So the total trip is going to take him 7.5 hours, not including stops that he makes. So, you're looking more, it depends on how long he stops, 8.5 hour trip if he stops again, or if he stops a couple more times, we're looking at maybe 9-hour trip. Now we need to graph it, and we need to start by labeling the x-axis and the y-axis. From our table, we already know that the x-axis is going to be time in hours, and the y-axis is going to be distance in miles. We also need to decide on numbers, and since the x-axis only goes to 4.5 hours, we can count by every other one. 1, 2, 3, 4, 5. The rule of thumb is to use more than half the graph left to right and up and down. Now up here I need to get up to 525, and if I count by 50s, so 50, 100, 150, 200, 50, 300, 50, 400, 50, 500, that's going to make it. So that's how I'm going to label. Now I do my best to plot those points, 0 to 10. Well, I know that's going to be just above the 200. That middle line in between the 200 and 300 is 250. At 3, 420. I try to stay even below halfway between, because that would be 25, but that's pretty close. I'm not going to worry about the 1.3, 300, but the 4.5, 525 I definitely want to do. That one I do want to be halfway between. And then I use a straight edge and I draw my line. And those points match up pretty well. They're pretty linear, so I did a pretty good job putting those on there. The nice thing, of course, about this line is that we could now look back at 2 hours. How long is it going to take him to go, or how far is he going to go? He'll be 350 miles, approximately 350 miles in at 2 more hours. At 5 hours, if he were to keep going, he would be past his destination. In 1 hour, in 1.5 hours, we can look at all of these and see how long is it going to take him to go exactly 400 miles. So we go over here and it hits the line right there. So it's a little more than 2.5. So that's the nice thing about the graph, is we can look at, we can predict other values if he keeps the same rate, 70 miles per hour.